Welcome to the lecture series on policy gradient methods. In this video, I present the basic idea of policy gradient. We are all familiar with TD methods such as Q-learning or SARSA. They start from a discrete graph with states S, another state S prime that are connected by actions. There are transition probabilities. Now, for continuous states, Q-learning is no longer that good because function approximation is necessary. You may say function approximation. What's the problem? We just take your neural network. It's a great function approximator. Well, it turns out it's potentially unstable because if you change with a function approximator, if you change the weights of the network, if you change the parameters, then you always change also neighboring states. This might be good for generalization, but it might do the wrong generalization, and that makes it unstable. Now, even in fully observable Markov settings, these kind of discrete settings like on the graph, off-policy TD methods like Q-learning can diverge using function approximation. Again, because function approximator links states that maybe should not be linked, it's not necessarily stable. It gets worse if you have partially observable environments. That means non-Markovian. You cannot distinguish two states just from the present observation. Then TD learning algorithms become really problematic. And while previously I've talked about continuous states, it even gets worse if you have continuous actions. Well, the source of all these problems is that the world is not a Markov process of this type. The world is not fully observable, and the world is not tabular. It's not just existing of discrete states. So with policy gradient methods, the basic idea is that we forget about Q values. We optimize directly the reward. We associated actions with stimuli stochastically. So let me just compare the two philosophies. In Q-learning, we build a table. For each state action pair, we assign a Q value. And so, for example, for state 2 and action 1, we have a Q value, Q of S2 and action 1. And then with this Q value, we play around. We use epsilon greedy, or we use softmax methods to choose the best actions, to build a policy. Now instead, we can have a table in policy gradient that says we directly associate each state with the probability of action giving a state. So, for example, again, I'm in state 2. I have 3 actions, and the 3 actions together are taken with certain probabilities, and the only condition is that these probabilities must sum to 1. And now the idea is that these table entries, these probabilities of action given a state, will actually depend on parameters. And so now we change the parameters so as to maximize the rewards. So we can write this stochastic policy. The action depends on the state, and it also depends on parameters. So what we really show in this table over here is this stochastic policy P for an action given the state, and that all this depends on parameters. So I write here the parameters explicitly in terms of an entry in this function here. You could also write it in that form, P of A given S, and then the whole thing depends on parameters, and these parameters I could also write as an index down here. It's just two different notations, and in both cases, it's really the same thing. So just to summarize this basic idea of policy gradient, we have a stochastic policy. It's denoted as a policy P that depends on parameters. So if the policy is directly the probability of taking an action in a certain state, and then we change these parameters such as to maximize the rewards. And what's different from TD learning, there's no need for any Q values or V values.